Hello, General Chemistry Tribe. Today, in this lecture, we are still talking about aqueous ionic equilibria, and we're in the, basically the third portion of this. We've talked about buffers, we've talked about titrations, and now we are talking about slightly soluble solids. And so you may remember this idea of precipitation reactions. And so, as far as, maybe a slight review of precipitation reactions, we would have, basically two different starting materials, such as lead nitrate, that's aqueous, plus sodium, or let's say potassium iodide, that's aqueous. And this would give rise to a reaction where we would have precipitation occur. The two possible products that we would get would be lead iodide as well as potassium nitrate. And remember, we had to then, predict, phase. Right, we had to predict that for the lead iodide that would actually be a solid, and for the potassium nitrate that would be aqueous. So that led us to then the actual precipitation reaction, which would be looking at just the, the actual players, the ones that are actually reacting. Meaning that we could start with lead, that's aqueous, in that +2 state, plus 2 iodides that are also aqueous, and that produces lead iodide as a solid. This was our, net ionic reaction when looking at precipitation processes. Here is an old video that I showed in the first part of general chemistry, just to kind of refresh our memory as to the precipitation reaction. So in that video, we had the lead nitrate, which was basically the test tube at the bottom. Or the test tube solution. And then our potassium iodide was added dropwise. Basically to that test tube solution, or to the test tube. And what we ended up with was our lead iodide, which was that brilliant yellow color. And that's the general, quick review of precipitation reactions. When we get into looking at these processes, really these solid products have slight solubility. And basically that solubility is governed by an equilibrium process. So basically all these precipitation reactions that we've talked about earlier in the first part of general chemistry are really equilibrium processes. And so we now have to understand how to really write those processes and really describe these reactions, not in the sense of a one-way process that we've discussed earlier, but more in the ways of an actual back and forth or an equilibrium process. So for some, general rules with slightly soluble solids, first rule is basically that the equilibrium reaction is written in terms of the solid. Basically that means solid is the starting material along with water, much like our acid-base chemistry. The products are basically the ions that result from the slightly soluble solid. So that's the first rule. So as an example of that, we could talk about silver chloride as a solid. It is one of these that falls into our category of slightly soluble solids. Remember that chlorides tend to be soluble in molecules, like sodium chloride, for instance. But silver was one of those exceptions. Silver chloride, lead chloride, as well as mercury type halides, are all these types of solids that fall out. So that goes back to our first example with the video inlay with the lead iodide, right? That was one of those solids that falls out. So silver chloride is another one of these solids that falls out of solution upon a precipitation type process. So we would want to write that in terms of the solid starting material. We have H2O as well for the other starting material, and now we're just showing the ions that dissociate upon that solid going into solution. And so here we have our silver ion and our chloride ion being produced. And this is an equilibrium, just like all these other equilibriums that we've talked about. Now we have another one. We've gone from Kc to Kp to Ka to Kb, and now we have Ksp. And Ksp is the solubility product equilibrium constant. And, you know, there's nothing new here as far as big K, except for the fact that we have this solubility product idea, or slightly soluble solid idea. So our KSP is just like we've done in the past, right? That our KSP is still equal to, you know, the idea of our products over our starting materials. And so in this case, we would have, you know, the silver plus 1 as a product, the chloride minus 1 as a product. But if we go to the starting material side, right, there's actually nothing there that would be part of K. We have a solid, silver chloride, so that's not part of K. No concentration, no pressure. And then we have water, which we have seen before with Ka and Kb are not part of the equilibrium constant, right, because it's a pure liquid. And as a result, doesn't have a concentration either. And so our KSP for this type of process would just be looking at the ions that are in solution. So KSP basically, you know, dictates the saturation point in the solution. And we'll come back to that later with this idea of Q versus K. So that's the first rule, is that with looking at equilibrium processes for slightly soluble solids, we're always writing that in terms of the solid starting material and how that actually dissolves into solution, into an aqueous solution, to generate those specific ions. The second piece to our rules is this idea of molar solubility. Molar solubility is really given this, you know, moniker of S, but really this is just molarity, or moles of our solute per liter of solution. But we do have this kind of different letter, if you will, you know, as far as talking about molar solubility with slightly soluble solids, we always have this capital S. The molar solubility is always in terms of the starting solid. The ions in solution can be expressed in terms of this idea of S, or molar solubility. so long as you're careful with molecular formula stoichiometry. So if we can continue kind of this example of the silver chloride. If we have, let's say, the molar solubility of silver chloride is 1 times 10 to the negative 4th molar. What is basically the concentration of both silver plus 1 in solution and chloride minus 1? So this would be looking at an example of, okay, I have a slightly soluble solid. Talking about the molar solubility of this material, molar solubility being important to that term. And so in our first question of, basically what do I have initial? I have this silver chloride solid material. All right, that's setting us up for then what is the equilibrium reaction? And now what is our KSP actually equal to? So I'm given our molar solubility of the silver chloride to be 1.0 times 10 to the minus 4th. So that is our molar solubility, or S, for that solid silver chloride. And then looking at the equilibrium reaction that results, and just to write it again, right, this is really just kind of like a conversion process that for every, 1 mole, or 1 molar of silver chloride that goes into solution, well, that would be equal to, right, the same idea as far as 1 mole or 1 molar silver plus 1 that would be in solution, or 1 mole or 1 molar chloride that would actually be in solution. So if our molar solubility of the silver chloride was equal to 1 times 10 to the negative 4th molar, that means that our concentration of silver plus 1 is also equal to that value, as well as our chloride species as well. And really that connection, between those two is really just the reaction stoichiometry. Right, just looking at the reaction, it's all 1 to 1 to 1. And so that's how we can simply relate this idea of this new term, molar solubility, to now concentration of the resultant ions in solution. So let's do, another example, but similar, but maybe just a little bit more difficult. So in this particular question, we just want to do something similar that we did earlier with silver chloride. We want to calculate the concentration of both ions present in solution when ferric sulfide dissolves in water. Ferric sulfide has a molar solubility of 1.2 times 10 to the negative 7th molar. So in just looking at how that equilibrium reaction what it looks like, is just, really showing the dissolution or the dissociation of that solid, in this case the ferric sulfide. And looking at the stoichiometry, we would have 2 irons that are +3, then we'd have 3 sulfides that are -2 on that product side, right? Both are actually aqueous. We could also talk about KSP. I mean, it's not really, technically necessary, for this particular reaction. But, we could represent that idea of KSP just to show you where we're going with this. Right, they would have a KSP expression, that would look something like this, and it's something that we'll reinforce in subsequent lectures. Again, just products over starting materials. Our products, notice that stoichiometry, very important as far as, the order with the iron and the sulfur being squared or cubed respectively. But no denominator, no starting materials in that representation, because our materials are solid, or they are actually pure liquid in terms of their phase. So the ferric sulfide is a solid, so it doesn't have a molarity, and the water is a pure liquid. It doesn't have a molarity either. So that's why we don't put that within the KSP expression, and that's getting a little ahead of ourselves here. Right now, we just want to basically figure out, the concentrations of both ions present in solution. So we're really looking for, the concentrations of these 2 ions, namely the iron +3, the ferric iron, and then the sulfide. And we also have this molar solubility. again, that's always in terms of that starting solid. So we actually know its solubility. So to get at these ions, we just need to use this, chemical reaction or equilibrium process to relate those two. That if we look at trying to solve for our iron plus 3 concentration, well, basically that would be 2 times S, right? That for every 1 molecule of the ferric sulfide solid, we get 2 of those iron plus 3 ions. So we would have 2 times that 1.2 times 10 to the negative 7th molar, or 2.4 times 10 to the negative 7th molar. And we can do the same process for our other ion that's present in solution, namely the sulfide. The sulfide would be really 3 times that molar solubility, right? Because for every 1 molecule of the ferric sulfide solid, I get 3 of those sulfide ions. So we just need to take that molar solubility and multiply it by 3. And so there is our concentrations of the ions present in solution based on that idea of the original molar solubility. So that's the introduction, this introduction into how we write equilibriums with slightly soluble solids, as well as this introduction to the definition of molar solubility and how it's always in terms of that starting solid material. And in the next lecture, we'll get into now how we can relate molar solubility to KSP.